Let's get started and let's look at some of the mathematics of the solutions unit, and particularly we're going to see how molarity, which is a measure of concentration, and stoichiometry can be combined to solve real-life problems. Now, if you've looked at some of my slides before, you realize I like to use this diagram. I call this, well, lots of different things. Mole island diagram. I call it my MVP because it combines mass and volume and particles of reactants. I also call it my little dirty birdie feet, and it on the left side here, this would be the first substance we're going to deal with, and then this would be the second substance we're going to deal with. Now, that's all in the past, and we've done stoichiometry using that. What we're now going to do is add molarity into our diagram. So as you recall, molarity, that's big M, is equal to moles of solute over liters of solvent. Now, if you manipulate this equation, you can multiply big M, molarity times volume, to get moles. So moles is equal to molarity times volume. Now I'm going to put that right into my mole island diagram. If I'm given the molarity and the volume of a substance, really I've been given the number of moles, and then I can work the stoichiometry problem. Now, if I'm given the mass of one substance, I can convert from that mass to moles of that substance, and then if I have a balanced chemical equation, I can go from moles of that substance to moles of another substance, and if I know moles of that substance, then I can get to the molarity or volume required. That's what we're going to do. Excuse me. So in this first equation, I'm combining lead 2 nitrate solution with potassium iodide solution. When this occurs, I produce the solid lead 2 iodide and an aqueous solution of potassium nitrate. Excuse me. The driving force for this reaction, of course, is the formation of the solid lead 2 iodide. Now, because this involves stoichiometry, I need a balanced chemical equation. Now, where I generally start balancing the equations is if I see a polyatomic ion. So I notice that I have 2 nitrates on the reactant side, and I have only 1 nitrate on the product side. So I'm going to go ahead and add a coefficient 2 in front of the potassium nitrate. Next, I notice that that gives me 2 potassiums, and I have only 1 potassium on the product side. So I'll add a coefficient 2 in front of the potassium iodide. Now I'm sort of like a cat chasing its tail, right? I got 2 I's. That's really a bad pun. Everybody has 2 I's, right? But 2 iodine here. And I have 2 I's over here. So that's okay. And I have 1 lead, and I have 1 lead. So it's balanced. If you want, you can go ahead and add coefficients 1. They're not needed. They are understood. Sometimes my students say those are the invisible ones. I'm not sure what that means, but I do kind of understand. All right, so here's our question. All right, what volume of 4 molar potassium iodide solution would be required to yield 89 grams of lead 2 iodide? Now, we're assuming that the lead 2 nitrate is in excess. Okay, so I'm going to get a new sheet of paper to start this one, and I'm going to write my equation down, and now I'm going to insert the information from the question. I'm trying to find out what volume of 4 molar potassium iodide solution is needed. So I'm going to write right under the Ki question mark, or X liters of 4 molar potassium iodide solution is required to yield 89 grams of lead 2 iodide. So my target here is 89 grams of lead 2 iodide. Now, initially what I'm going to do is set up the question to find maybe the moles of Ki. If I can find the moles of Ki and I know the molarity, I can then find the volume. So let's see. So here's our strategy. First step, we're going to find the moles of potassium iodide needed that would provide me or yield 89 grams of lead iodide. After we do that, the second part of our question, well, let's go ahead. We'll take one step at a time. So we're trying to find out, we're looking at here our strategy part 1. how many moles of potassium iodide is equal to 89 grams of lead 2 iodide? So my first step is going to be to go from grams of lead iodide to moles. So I use my periodic table. I look up, and lead weighs about 207 grams per mole. Iodine weighs about 127 grams per mole, times 2 is 254. If I add those numbers up, I get about 461 grams per mole for lead 2 iodide. The lead 2 iodide grams cancels above and below, like that. At this point, if I stop the problem, I would be at moles of lead 2 iodide, and I want to get to moles of Ki. So I have to cross that middle bridge going from moles of PbI2 to moles of Ki. So what would I use for that? What do you think? I think I heard you say you want to use the coefficients of the chemical equation. Now, if you really think I can hear you, you're probably crazier than I am, but I think your thought was correct. What we want to say is 1 mole of PbI2 will produce 2 moles of Ki. I said it a little backwards, but the ratio is okay. 2 moles of Ki will actually produce 1 mole of PbI2. So I set this up so that moles of PbI2 up here needs to go down here to have that unit cancel. So in the denominator, 1 mole of PbI2, and in the numerator, 2 moles of Ki. Notice that my moles of PbI2 up here and down here will cancel like that. If I stop now, I'm at moles of Ki, and what I'm trying to find is, why look, moles of Ki. So at this point, I type this into my calculator, and I find out I have 0.39 moles of Ki. So we've done the first part of the question, or at least our strategy to get to the answer. Now, using our answer of 0.39 moles of Ki, we're now going to find the volume of 4 molar Ki solution that would be required. So we've done the stoichiometry part of the question. Now we're going to do the solution molarity part. So here we go. I think you recall molarity, that's the big M, is equal to moles over liters. So now I can plug in some numbers here. Perhaps I'll rearrange the equation. So I did some algebra there to solve it. I like to do the algebra first. Liters then is equal to moles of solute divided by molarity. So now I can plug in my numbers. I had 0.39 moles of my solute, Ki, that goes on top, and we were told that the solution was 4 molar potassium iodide. That goes on the bottom. So when I punch that in my calculator, I find out I need 0.098 liters of 4 molar potassium iodide. How many milliliters do you think that would be? Do you remember that conversion? Is it 1,000 liters in 1 milliliter, or is it 1 milliliter is 1,000th of a liter? Maybe you remember it as 1,000 milliliters in a liter. I hope that's what you said. So if I move the decimal place 1, 2, 3, I would need 98 milliliters of 4 molar potassium iodide. All right, let's look at another problem. Okay, so here it says, how many milliliters of 0.5 molar copper sulfate will react with excess aluminum to produce 11 grams of copper? Well, that looks like a pretty difficult question to begin with. I think what we should do is probably come up with an equation first. What do you think? Yeah? Good idea. So tell me, if you can, because I do hear voices when you talk to me in my head, what am I going to react here? What's the reactants? I think you said copper sulfate and aluminum. Good. Now, do you think this is going to be a single replacement, a synthesis, a decomposition, a double replacement reaction? Yeah, I think single replacement's correct. We've got a single element here and a compound. So I'm going to look at my activity series and see, can aluminum replace copper? And sure enough, it can. So now I think I'm going to be producing here copper, and I have to figure out what's left over. So I notice that I have aluminum not showing up and sulfate not showing up on the product side. So I recall that aluminum is always a 3+ ion, and sulfate is a 2- ion. So when I put this together, I will end up with a compound Al2SO4 3. And that's an aqueous solution. Great. Now we have a equation. What else do we need to do with this equation in order to make it useful for doing stoichiometry? Does this give you a hint? Why did I draw these lines here? Sure, we have to balance it, don't we? Now, what I tell my students is always start with the polyatomic ions. I notice I have 3 SO4s, 3 sulfates on the product side, and only 1 here. So I'm going to go ahead and add a coefficient 3 in front of the copper sulfate. Okay? Next, I'm going to notice, well, I've got 2 aluminums here, so I probably need to put a 2 here. And I have 3 coppers, so I'll need a 3 here. So I'll just go ahead and add those in, and now we have a balanced equation. Next, I like to write the information from the question under my equation. So what am I trying to find out here? How many milliliters of half molar copper 2 sulfate? So right under the copper 2 sulfate, I'm going to write, well, I guess I'm going to write that I produced 11 grams of copper, and then I'll write I'm looking for the number of moles of this. Now, I did that because I remember, hey, in order to do stoichiometry, I deal with moles, not really molarity. Okay? So now I've got a regular gram to mole calculation. That should be a couple steps. So I set it up, what am I looking for? How many moles of copper sulfate equal to the number of grams of copper that I have. So my first step is to convert grams of copper into moles. Looking at the periodic table, I notice copper weighs 63.5 grams per mole. So grams of copper cancel like that. If I stop now, I'm at moles of copper, and I want to get to moles of copper sulfate. So what do I need to use to switch from substance A, copper, to substance B, copper sulfate? If you said use the coefficients from the balanced chemical equation, you are definitely thinking correctly. So I notice that 3 moles of copper will be produced for every 3 moles of copper sulfate that I use. Because I want moles of copper to cancel, I'm going to go ahead and put in the denominator the 3 moles of copper, and in the numerator 3 moles of copper 2 sulfate. Notice my moles of copper cancel just like that. Now if I stop, I'm at moles of copper 2 sulfate, and hey, look at, I wanted moles of copper 2 sulfate. The ones also would cancel, so I just basically take 11 divided by 63.5, and I get 0.173 moles of copper 2 sulfate. This is a stoichiometry part of the problem. Now we have to do the molarity or solution part of the equation. And so for this I use my equation, molarity, moles over liters. And I'll rearrange my equation. I'm solving for a volume because I'm given in the question the molarity. That's the number on the bottom. And I just found my moles. That's the number on the top. So I can substitute those numbers in and type that in my calculator, and I will get my answer. The answer for this is 0.346 liters is how much 0.5 molar copper sulfate I will need. I'm going to stop this recording now simply because it's getting a little long, and I'm going to break it up into a second one. So look for the next one, and we'll continue these problems.